I'd like to take a look at an example of an emission spectrum type question involving understanding the Bohr model of the atom. In this question, an electron in a lithium atom drops from the n equal 3 to the n equal 1 energy level, and the question is, what's the frequency of the emitted photon? So let's start by making this a little more concrete. To give us a picture of the selected energy levels in a lithium ion, and for this question, they describe an electron starting in the n equal to 3, so I'll just put a little dot representing the electron in the third energy level. And it says it drops to the first energy level. So it's going to make a transition from there all the way down to the first energy level down here. Ends up there. So this really kind of involves, first of all, conceptually understanding that when we make that transition, we're really looking at a change in energy for this electron. And we can calculate the change in energy by using kind of this basic understanding that the final minus the initial energy should give us our change in energy. Let's see how that works out for this kind of a question. The final energy is negative 5.1 electron volts. The initial energy is 1.7, better yet, negative 1.7 electron volts. And so when we find the difference between the two, we get negative 3.4 electron volts as the change in energy. So if you look at this gap here, that's what we're really saying is the gap between this energy here and this energy here represents a drop of 3.4 or negative 3.4 going from there to there. So we want to make sure that not only do we have the ability to do the mathematics, but it also makes conceptual sense. Since we're working in electron volts, it really does make it easier to see how these numbers are coming together to give us this actual change in energy of this electron. So there's step one. We have the change in energy of the electron. And our understanding of the Bohr model would say that when that electron makes that transition and it loses 3.4 electron volts, it's got to emit some energy in the form of a photon. And that's why it can go from a higher energy level to a lower energy level. So once we've established that that's the change in energy for the electron, that also corresponds to the energy that's emitted by the photon. So just wrote this basic relationship here. It's really like a law of conservation of energy, but for whatever energy the electron wants to give up, the photon has to be emitted with that energy. So when we make that connection, we can now use the relationship between the photon energy and frequency in order to calculate the frequency. Our photon energy is 3.4 electron volts. Now, you'll say, well, this is negative. I'm going to make this positive because this represents a loss in energy for the electron, but conservation of energy says if the electron's losing that energy, then the photon's gaining it. So I'm just going to put 3.4 electron volts as the energy of the photon. We're going to use Planck's constant, but careful to use the electron volt version of Planck's constant. So 4.14 times 10 to the minus 15 electron volts times seconds. And now we can use that to find the frequency. Gives us a frequency of 8.2 times 10 to the 8.2 times 10 to the 14 hertz. And so we can see then the connection between the loss of energy of the electron, and if it's going to lose energy, to obey the law of conservation of energy, whatever energy the electron loses, that's the energy that shows up in the form of a photon that's emitted. And if you want to take it one step further, you could try and predict what kind of wavelength of light. Now I'm going to make a quick comment on this energy map here that we have for lithium. You'll notice that it's all in the negatives. And this is not an uncommon way of talking about energy with electrons in atoms. It's almost synonymous with considering in a mechanical system, if we have a ball at the surface and then the ball at the bottom of a well, we could certainly talk about this ball up here having 0 joules of energy, and then when it falls into the well, it has to have like negative energy. Maybe it has negative 10 joules of energy. And that's okay because we're talking about potential energies, just like we would be talking about with these electrons. It's okay for us to end up with negative energies. It doesn't make energy a vector. It just means that compared to a certain location, this object has less energy, 10 joules less energy. So we would represent that as negative 10 joules. So when you see these ways of describing the energy of electrons in energy levels, don't be surprised when you see these things in the negative. What that would mean then is if you could totally remove this electron, take this electron and totally remove it, it would have energy relative to the electron of 0 joules. In other words, if you ionize this electron, it'll have 0 joules. So just wanted to comment on the the way that often people will show the relative energy in an atom, usually use these negative energies. Don't be surprised. Just roll with it. Math still works because, again, to go from negative 5.1 up to 1.7, we would have to add 3.4 electron volts, or we lose it when we drop down. All right, so I would suggest you try a few examples on your own, get familiar with the wording of questions, but also relating the changes in energy to the electron and the emitted photons, and get used to seeing potential energies of electrons in energy levels of atoms being shown as negative values.